Good morning, everyone. Today's calculus lesson is going to focus on the topic of differentiability. So I'm going to go ahead and read through numbers 1 to 5. You can read along with me, or you can pause the video and read for yourself, and we'll catch back up after I read number 5. Okay, number 1, differentiable means that the derivative exists. Differentiable means that the derivative exists. A tangent line, just one tangent line, can be drawn at a point. This tangent line represents the slope of the curve at that point. Number 2, a function has a derivative at a specified value of x if and only if the slopes of the tangent lines from the left, which we call the left-hand derivative, are approaching the same value as the slopes of the tangent lines from the right-hand derivative. Number 3, if a function is differentiable at a point, it will automatically be continuous at that point. Differentiability implies continuity. Number 4, if a function is not continuous at a point, it will not be differentiable at that point. How can you draw a tangent line at a point where you must already pick up your pencil? Okay, and number 5, if a function is continuous at a point, it may or may not be differentiable at that point. One-sided derivatives need to be checked to prove or disprove differentiability at that point. Okay, so that's a lot of information. Underneath number 5, what I want you to draw, this is just a helpful little tool to help you remember this little trick. If you give me a bigger circle here, and then inside a smaller circle. Okay, in the outer circle, I want you to write continuous. And in the inner circle, I want you to write differentiable. Kind of have to make that circle big, that's a long word. So the inner circle holds the word differentiable, the outer circle holds the word continuous. And what I want you to understand is this. You have a function, f of x, somewhere out here that you're starting to look at, to analyze, to work on. If you take your function and you choose a point, you choose a value of x, and you test that value of x for continuity, that will get you in here. That will get your f of x in the outer ring of continuity. Once you prove continuity, you can then move on and try to test differentiability. And maybe you get in here, maybe you don't. Continuity does not necessarily imply differentiability. You can be continuous and not differentiable. You have to check both. But if it's the opposite, if you work from the inside out, if your function, if you prove differentiability first, then your function will automatically be continuous. Okay? If you can draw a tangent line to a graph at a value of x, then you can automatically assume that your function is also continuous there. Okay? So that little graph helps. As far as number 4 goes, what we said here, if you have a discontinuity, say you have a removable discontinuity in your graph. So you have this hole here, and we'll call this A. So if you have this situation going on, you're not continuous at A, okay, because of the discontinuity, which is removable. So if you're not continuous, you could never, how could I draw a tangent line at this point when there's no point filled in there? So that would be an example of, if you're out here and you can't even get to continuity, you're most certainly not getting to differentiability. Okay, so let's look at number 6. There are 4 scenarios that will alert you to a function being non-differentiable at a point. And they are called a corner, a cusp, a discontinuity, and a vertical tangent. These are the 4. So we're going to write these down. So bullet number 1 is a corner. Now let me show you an example of a corner. Actually, I'm going to pull my TI here. If we situate the TI here, if I turn it on, I've already typed in negative absolute value of x minus 2 plus 4. So if I graph that, you're going to see a sharp corner, which you know absolute value functions do have corners. So you see this sharp corner here at 2, 4. So let's just sketch that down, just a sketch, onto our paper. So we don't need the equation necessarily. We're just going to draw the graph. So here's x and here's y. And let's just draw this function that's got a corner, like right here. Okay? So that's the corner. The reason, and we'll call this A. So the reason that we're non-differentiable, at A is because if you look, the slopes of the tangent lines coming in from the left are positive and they're unchanging. They stay steady all the way in. You have positive slopes. If you look at the slopes of the tangent lines coming into A from the right, they are negative and they are unchanging. When you reach this corner, if someone said, hey, draw a tangent line there, well, do I draw a positive sloping tangent line or do I draw a negative sloping tangent line? They're fighting against each other here. And so because we can't draw one single tangent line at A, we consider a corner to be non-differentiable. Now, people will say, I'm just going to come over here to the side. This is sort of like, I don't know if I would necessarily draw this on your paper because it could be confusing, but I just want to show you now. So people will say to me, or students will say, well, then why is it that a quadratic would be differentiable at the vertex? I mean, isn't that sort of like the same thing? It's not. The reason that a quadratic is differentiable at the vertex is because it's a smooth, curved function coming into this vertex, and what ends up happening is, even though the slopes of the tangents coming in from the left are positive and the slopes of the tangent lines coming in from the right are negative, they're both approaching 0. So because of this smoothness, these are actually getting less steep and less steep and less steep, and eventually approaching 0 from both sides. See that changing slope? When you are linear on either side, you're not changing, not changing, not changing, not changing, not changing, still not changing. Same thing over here. So there's no nice leveling to 0, and that's the difference between a corner and something that is differentiable, like a quadratic. Okay, the second visual cue is a cusp. Now, a cusp, a little different from a corner in the look of it. Let's go to y equals, and this time I'm going to type in x raised to the 2/3 power. Okay, x raised to the 2/3 power. If I graph that, this is what you get. This is called a cusp. See how it kind of arches in here, drops, and then curves back up? It almost reminds me of when I was in elementary school and I would draw birds in the sky. So a cusp looks like this. Here's my x, here's my y. So my cusp kind of arches out this way, arches out that way. Okay, so why is that non-differentiable? Well, the reason is the slopes that are coming into, we'll call A this point at 0, 0. The slopes that are coming in from the left side, so you see them here, slope, slope, slope. Same thing from the right. These slopes, do you see how they're getting steeper, 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 steeper from the left, and steeper, 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 steeper from the right? These tangent lines are approaching vertical, and the slope of a vertical line is undefined. So this is the reason we are non-differentiable at 0, 0 here with the cusp. So anytime you see cusps, you're non-differentiable there. Okay, the next one is a discontinuity, any kind of discontinuity. And this is basically kind of reiterating what I said up here. If you can't get continuous, you definitely can't get differentiable. So any kind of discontinuity, we could draw lots of them here. Say you have just what I drew upstairs there, just removable discontinuity. That's a visual cue that you're non-differentiable at A. You could have a jump discontinuity at A, maybe something like that. How are you going to draw a tangent line there? Where are you going to draw it? Here, here, discontinuity, no tangent line. And then the final visual cue is a vertical tangent line. And a vertical tangent line would be something like this. If you graph x to the 1/3 power, bring this back on here, x raised to the 1/3 power, graph, see what this looks like here. See at 0, 0, coming down through here, and then right here at 0, 0, we're approaching vertical. So it's going to look like this. If you ever see anything coming through and then the tangent lines are approaching vertical just for a moment and then they carry on their merry way, then right at this point, we'll call A, we are non-differentiable because the tangent lines, again, are approaching vertical from the right and the tangent lines are approaching vertical from the left. So if you visually see any of these cues on a graph, you can just say that the function is non-differentiable at A. All right, if we flip the page, we have one last example we're going to do on this video. So let's read it here. Differentiability implies local linearity. Functions which are differentiable, able to be approximated by a tangent line locally, will appear linear as you zoom in at a particular point. All differentiable functions appear linear if you zoom in far enough. Non-differentiable functions will not straighten out because they cannot be approximated by a tangent line, okay? So we're going to look at the difference here between the graph of y equals the absolute value of x and y equals x squared. And what we're going to do with those, which I'm going to show on the TI in a second, is we're going to zoom in many times to see one of them straightening out and one of them remaining unchanged. So let's go back to our TI. And clear out the old stuff. In the first y1, I'm going to type in absolute value of x, and in y2, I'm just going to type in the quadratic x squared. Okay, so when I graph those in a normal view window, you see that corner, and then you see the parabola. Okay, my visual cues from the previous page would tell me that the v is the non-differentiable one because the slopes from the left are harsh negative, the slopes from the right are harsh positive, and I know that's the one that's not going to be differentiable. But let me show you something else. If you hit zoom and you go to number 2, zoom in, hit enter, and where do you want to zoom in?
11 skaters in the following management teams.
Pardon the interruption.
LGI, rooms 112 and 114 for hearing screening. Mrs. Whitley, room 204. Mrs. Scanlon, room 205. Mr. Brasati, room 206. Mrs. Nykirk, room 207, Ms. Rivera, room 209, Mrs. Mead, room 210, and Mrs. Longacre, room 214. Again, those students, please report at this time to LGI. Thank you.
Okay, sorry about the interruption. So we hit zoom in, and now down here it says 0, 0. That's where my cursor is blinking, and actually that is where I want to zoom in. I want to look at what's happening at this corner, so I'm just going to hit enter. Now what you can see is the V shape is still there, the quadratic, the curve is still there, so not much changing there. Let's zoom in again. Zoom in at 0, 0, hit enter. There's my V, and there's my parabola. Okay, let's do it again. Zoom in, right at 0, 0. There's my V, and there's my parabola. Zoom in again. Look at that V, unchanging. But where's the parabola going? The parabola is beginning to disappear as I zoom in at 0, 0. I'm going to do it another time. And now the parabola has completely disappeared. So here's my final thought on this lesson on differentiability. If a function is non-differentiable, okay, like this one, We know that corners are non-differentiable. If that is the case, you can zoom in, get as close to the origin as you can, and that function will look exactly the same zoomed in as it did zoomed out. It's unchanging, and it cannot be approximated by a tangent line. See, this doesn't look anything like a line. However, if a function is differentiable, okay, so let's go back to the paper here. If the function is differentiable, let me just kind of draw right here. Okay, so here's your parabola, the one that is differentiable, right? Here it is. As you zoom in really, really, really close to the point that you're curious about, that function, if it's differentiable, will appear linear because in that vicinity, locally, in the vicinity of 0, 0, the closer and closer you pull into 0, 0, the more and more the function resembles the tangent line which approximates it. It actually looks linear. But that v, that non-differentiable function, boy oh boy, that is staying steady and looking like the v because it will never be approximated by a single tangent line. And that's what differentiability is all about. So I hope that makes sense. And on the next video, we're going to tackle one-sided derivatives.